So in 1.2, we're going to be taking a look at solving problems using the trigonometric ratios. So more of the application questions. So what we're going to do is just take a look. This is the first page right directly out of the textbook, okay, for 1.2. And if we look at what we've got in here, what it says is basically the heights of some structures are best determined using trigonometry rather than a measuring tape. Basically the structures that are very large. Okay, so for example, a person could stand a certain distance from the base of the CN tower and use a clinometer to determine the angle of elevation to the top of a tower. Now, what is this clinometer that we're talking about here? I've got a picture of a simple one right here. And basically what we've got here is the protractor. So the protractor itself has all the angle measures, and depending on where you measure, you either start here at the 0 on this side or you start at the 0 on this side as well. Okay, you're looking at basically starting level. Horizontal is at 0, so if you're looking at the horizontal line, that's at 0 degrees right there. All right. What you would normally do with this, and this is like a picture of a homemade clinometer there. You've got a straw and you put your eye gaze through the straw so that at the other end, whatever object you are looking at, the top of, and in the case of the example above was the CN tower. I can't draw the CN tower, so I'm not going to, but you've got the top of the CN tower, there's whatever it is, and it goes out that way. So you're looking at the very top in that one. When you can see it through the straw, through your eye gaze, you then look and measure at what is the angle that you see on the clinometer. And this one looks like we've got an angle of 70 degrees. And that's how you read it there. Okay, so that's the idea. Now there are fancier ones out there that other industry people do use. Okay, for example, as I said, the clinometer is measuring the angle of the line of sight above or below the horizontal, and it's used by construction workers, okay, to measure the grade angles. It's or forestry workers to measure the heights of trees, and even movie directors measure the sun's elevation, okay, at times. And the last one here, satellite antenna installers to locate different satellites. Okay, so it's got a broad range of usage. All right. A couple of the terms that we need to look at here. First of all, when we're dealing with angles from a horizontal, we call those either the angle of elevation or the angle of depression. All right. Now, as we label the angles, if it's an angle of elevation, you can see that it's from the horizontal going up. All right. So from the horizontal up gives you the angle of elevation. All right. In this case, the boy's height up to where he sees the airplane. And in the angle of depression, the angle between the horizontal and the line of sight from the observer's eye below eye level. So it is down. So from the horizontal down, that would be the angle there of depression. And we label the angles like we did last lesson, okay, with theta here. All right. So those are the ideas there that we've got to sort of look at: the angle of elevation, the angle of depression, for a variety of different questions. One example that we could do, all right, and very quickly, what we have is if we are going to measure, let's say, the outside, one of the outside flagpoles that we have outside of the school, all right, we have a flagpole. We'll do the little flag. My awesome drawing of a flag there. There's my quick drawing of the maple leaf. All right. We stand a certain distance away, and here is the person looking at it with a clinometer at eye level. Okay. So let's try to figure out the height of the flagpole. If we know certain things, we can take the distance between ourselves and the base of the flagpole, and we can say that that happens to be a distance of, let's say, 5 meters. Okay? We know that when we look at the horizontal, all right, we use a clinometer, and we look at the horizontal, and we look through and we see that the angle of elevation to the top of the flagpole from the horizontal up happens to be at 5 meters. It could be somewhere around, let's say it's 42 degrees. Okay? If it happens to be that, that's fine. Well, there's a couple things that we know in this case. Everything to the ground is perpendicular to the ground. It's at 90 degrees. So we have it 90 degrees from the flagpole to the ground. Well, the ground is assumed to be horizontal. So our horizontal here is also going to be 90 degrees to the flagpole. Since the bottom rectangle is a rectangle and the distance from the flagpole to us is 5 meters, we know that the distance on the base of this triangle through the horizontal here is also 5 meters long. All right. So what we're trying to do is we're trying to find out what is the total height of the flagpole from the top of the flagpole to the ground here. Notice we have this extra piece right here, which is basically our height, or it's our eye height. So eye level, where we look through the clinometer to see that it's 42 degrees up to the top. Well, we'll guess at that, and we'll just say that it's a person that might be 1.7 meters tall at eye level. So we know that this is 1.7 meters as well. So how do we find the remaining portion of the flagpole? Well, we go back to the primary trig that we looked at yesterday, and what we do is we say, okay, in this example, what are we given? All right, well, everything you know is according to the angle itself. We've got a 42 degrees, so that's our angle. We have that given to us. And from the angle to this side, we can see that that's the adjacent side length. All right. What is it that we need? We need to find, well, again, x, we look across, it is across or opposite the angle itself. So that is the opposite. All right. That's the opposite side length. And when we look back at what primary trig ratio we need to use, okay, the only one that uses the opposite and adjacent with the angle would be the tan theta, because it is opposite over adjacent. So we're going to use the tan, okay, of the angle of 42 to calculate what the x is. Now the x is in the place of opposite. We've got the adjacent at 5. And so when we multiply the 5 on both sides, we get 5 times the tan of 42 is equal our x value. All right. So you punch that into your calculator. 5 times the tan of 42 in my calculator. All right. 5 times tan of 42 is approximately 4.5 meters. Okay. Now that 4.5 is where x is. That's the 4.5 right here. So the total height of the flagpole is the 4.5 plus the 1.7. Okay? So we can say, therefore, the total height of the flagpole is 4.5, 1.7 is 6.2 meters tall. Okay, so that's one way that we can use our trig in order to figure out certain distances that are considered inaccessible distances. All right, inaccessible distances. I think the textbook gives you some really good situations where you can't just climb up and use a use a tape measure, for example, the tree heights and things like that. Okay, and there are other examples that we can do as well. We'll finish off. We'll do another example. All right. And maybe this example might say something to the effect of use the angle of elevation or the angle of depression. All right. If we say, um, let's say John is 15 meters, okay, from the base of a building. We'll just go with a simple building. Okay, base of a building. The angle of elevation to the top of the building is 37 degrees. Okay? What is the height of the building? Okay? So in this case, you draw the diagram, right? John is over here. He's 15 meters away from a building. All right? The angle of elevation. Now, you could do eye height and say, okay, we have to add a little bit, but because it doesn't give us any height for this John, we're going to say that the angle of elevation starts at his feet. And the angle of elevation, remember, is from the horizontal. Remember, this is horizontal up. And so this is the 37 degrees there. All right. Again, we're talking about the ground to a building, so it is a 90-degree angle always. We assume that unless otherwise stated. And from there, we then have to say, well, we look for the height of the building. We'll call that x over here. Again, what are we given? What do we need? And finally, what do we use? All right. So what are we given in this case? Well, we're given the angle and we're given this side length. This side length, remember, is adjacent. Right? So we've got the angle, we've got adjacent. What are we looking for? Right? Well, the x is way over here on this side. It is opposite the angle. So we are looking for, or we need, the opposite side length. And again, just like the last example, tan is the trig that we use. Okay? So again, it's practice. We have the tan of 37 degrees equals our x over 15, which is the opposite. Multiply both sides by 15 to get you your x value. So 15 times the tan of 37. Hopefully you're doing this with your calculators, and you get 11.3 meters. Okay, therefore the height of the building is 11.3 meters. Okay, so it's not a very tall building. All right, as buildings go. All right. One more thing I wanted to show you, another example, and we'll make it somewhat different without all the words, going through it. I'll just kind of draw my pictures here. One of the things you might have is, we've done before is, here you are and you're in a hot air balloon, right? So now you're in the air somewhere. Okay. If we know, because somehow you've got a measurement device that tells you what your altitude is, and it says that you are maybe 200 meters high in the air. Okay, so your altitude is 200 meters there. Again, from where you are, it's 90 degrees straight down. Okay, what we can do here is say, well, from your distance from where you are over to this object, somewhere over here on the road, okay, a direct line distance, okay, of, let's say it's 450 meters. All right. What we want to figure out in this question is what is the angle of depression? Now, here's a thing to take note of all the time. Again, the angle of depression is from the horizontal down. So you're looking for this angle right there. Now, one of the things that you're going to use a lot, okay, is that angle right there is the same as this angle here. If you remember the Z pattern, okay, the Z pattern, two parallel lines cut with the transversal. Z pattern gives you equal angles, okay, in that case. So what you could do is you can just calculate the triangle from below and try to figure out what the angle is that way. So again, what I would do in this case is I would take a look at what is given, what do we need, and what do we use. All right, and it's all based on from the angle. Now in this case, we need the angle. We don't have it there. We know that opposite the angle itself is what's given to us as the 200. And we're also given the side length that's opposite the right angle, which we know to be the hypotenuse. So when we look at the three trig ratios, all right, we try to figure out which one it is that uses the angle, the opposite, and hypotenuse. And hopefully you come up with the sine, okay? The sine of an angle is equal to the opposite side length divided by the hypotenuse. So again, let's take a look. The sine of the angle we need is the opposite, which is 200 divided by the hypotenuse, which is 450. Now we want to isolate for the angle itself, for theta. So again, what we do is we take the sine inverse from both sides and we write it down like this, the sine inverse. So we have to take the time with our calculator to figure out how to calculate that sine inverse correctly. So I want you to be able to play with it. I know there's a couple of examples in the textbook on the left-hand side of the section pages around page 19 or 20 that it gives you a couple of ways to try to figure this out, but hopefully you figured this out before today. If you did it correctly, you should get approximately 30 or 26.39 degrees. So therefore, the angle of depression is 26.39 degrees. Okay, so that's a couple of examples there. You can always go back to look at the video again to see, okay, how I did certain things. All right, as you're going through your work. All right, and here is the work that you can do, all right, for this section.